In the second part of Chapter 9, we look at how, in particular, volatility is changing through time and how this affects our Black-Scholes formula to price put and call options. So in the Black-Scholes formula, we assume that asset returns are unconditionally normally distributed and they don't have any large jumps. So they don't suddenly have very high returns or very low return realizations. And this is, however, not quite true in the real world. In the real world, we see that unconditionally returns are not normally distributed. And in particular, we typically see that we have very fat tails, meaning that we have very high returns at some points and sometimes very high negative returns. And these very large positive or negative returns are difficult to reconcile with a normal distribution, because under a normal distribution there would be basically a probability of 0 that these returns would ever realize. Now, having these kind of fat tails or very large positive or negative return realizations could be due to different reasons. So one reason could be, well, there might be some jumps and maybe returns are not just following a normal distribution. Or it could be that the conditional volatility is changing through time, and sometimes volatility is just much higher than during other times, and during these high volatile times then you can get very large realizations, either positive or negative returns. What we know from the data is that we do have these returns, and there are many different models which try to explain that. And one of the very popular models is called the Garge model, and that's actually a model where Robert Engel earned the Nobel Prize in economics to model these volatilities. So let's look at some of the data. Here I have a histogram of US stock returns. These are daily returns between 1926 and 2010. The histogram basically measures how many returns do we have, for example, here close to 0, and we see that we have many daily returns which are very close to 0. Then over here we see how many daily returns do we have which are plus 5%. Well, there are not so many. Similar at minus 5%, there are not so many daily returns. And then we see that there are some very few observations, very few days where we get really large positive returns, or also some really large negative returns. Now, the red line over here, which you see is kind of very thin drawn, that would be a normal distribution to match the expected or average daily returns and also the standard deviation of these daily returns. Now, clearly you see that these blue bars indicate that there are many more daily returns which are close to 0 than what this normal distribution suggests. The normal distribution would say, well, there should be only about this many daily returns which are close to 0. On the other side, if we are anywhere between like 0 and 5%, plus or minus 5%, then we see that the normal distribution would say, well, these daily returns should appear much more often in the data than what we actually see according to these blue bars. So there seems to be a little bit too few probability for returns of about 1 to 3% or minus 1 to 3%. And then finally we see these extreme return realizations. There should be basically a 0 probability of that happening. According to the normal distribution, we should never see, or basically almost never see, these type of realizations of really large positive or really large negative daily returns. So particularly this one over here, that should really never happen. And also you see kind of at around minus 5% mark, you have way too many of these blue bars. That means too many realizations where you get these large negative returns on a day, much larger than what should be possible under normal distribution. The figure over here is again these daily returns. All I'm doing is I zoom in a little bit so the scale changes. Before we had minus 20% all the way to plus 20% of daily returns. Now I look just in that window between minus 6 to plus 6. And again, what I want to illustrate is that just even between like plus 4 to 5-6%, you have too many realizations. And also similar between minus 4% and minus 6%, you have too many realizations in the data of daily returns, many more than what should be plausible or possible under this red normal distribution. We can also look at the time series of daily returns. So here, for example, we see we have almost plus 5% daily return. Here we have about minus 6 or 7% daily return. Here we have one of these very large negative daily returns. This one is actually a daily return really large positive. This goes again from 1926 to 2010. And the interesting thing which you see is that there's some times, like for example around here, where these daily returns go up and down quite a lot. So there seems to be a lot of risk and a lot of volatility. And then there are these times over here where daily returns are very close to zero. And it seems like for this time horizon, volatility was relatively low, which is then again followed by a period where daily returns are kind of more positive and negative, which means again more risk, more volatility, and then again there is a more quiet time horizon where returns are again closer to zero and risk or volatility is lower. So you see kind of you have these episodes of a lot of risk, not much risk, again quite a lot of risk, not that much risk, and so that's changing through time. And a similar picture can be shown here where I take daily returns and I square them. That's kind of a very simple approximation of volatility. And again, you see here, these squared returns are quite high during these times, indicating that we either had very large positive or very large negative returns. And then we have an episode where squared returns are small, meaning again, these returns are close to zero. Again, not that much volatility, followed again by quite volatile times, and then again times with little volatility, and so forth. So again, this just illustrates that in the data, it seems like risk is changing through time or volatility is not constant. In the Black-Scholes formula, we know that volatility is a crucial input factor to determine the price of a call or a put option. Now the problem again is that volatility is not directly observed. We actually have to estimate it from the data, and as I have illustrated in the previous slides, this volatility appears to be changing through time. Now this is a bit a challenge, because if you don't know exactly what volatility is, then how can we use our Black-Scholes formula to actually pin down the price of the option? One thing is true in the Black-Scholes formula, that's that the volatility and the option price are in a one-to-one relationship. So if the volatility is low, then the option price is low. If the volatility is high, then option price is high. So in other words, the option price is strictly increasing in volatility. And that's true for both put and call option. And that also goes back to what we have seen about these Greek letters. When we looked at Vega, Vega was always positive, and actually the same for put and call options. Kind of saying that if risk goes up, if volatility increases, then this price increases. This one-to-one relationship between option price and volatility can now be used to basically back out from market prices. So from the actual observed traded prices of put and call options, we can back out what the market believes should be the volatility of that underlying asset. What's the rationale here? Well, basically we're saying if people are willing to pay an X amount of dollars for a call option, then that should be really the price which people think is fair, or kind of reflect what the market believes are the current condition, financial markets, whether markets are healthy or unhealthy, are they risky or not. And so taking this market view, using that price which is believed to be fair in the market, then we can back out what the market belief is about the volatility for that underlying asset. We will see in the next few slides that if you compute this implied volatility for market prices, then we find that the volatility actually depends on how deep an option is in the money. And so that thing is what we call a volatility smile, and I'm going to explain in a minute exactly what that means. Now let's look first at how we can actually compute implied volatility. Suppose you have a current stock price of the company XYZ, which is $100. Risk-free interest rate is constant and 2% per year, continuously compounded. Suppose we would like to figure out what is the implied volatility over the next 3 months of that stock XYZ. If we have an at-the-money call option with 3 months left to maturity, and the price at which this is traded is $4.23.216. What does it mean at the money option? It means that the strike price is also $100. It's the same as the price of the underlying asset today. So now how can we do that? So we basically use our Black-Scholes formula. We see the price of the call, which we actually observe now in the market, this $4.23.216. That's equal to the price of the underlying asset times that probability that the call is going to be in the money under the Q star probability measure minus the present value of the strike price times the probability that the call option is in the money under the risk neutral probability measure Q. Now again, how do we find these threshold values D1 and D2? These guys depend on the price of underlying asset and the strike price. It depends on the time to maturity, the 3 months. Depends on the risk-free rate, and now it depends on that volatility here and here. And also for D2, again, it depends on that volatility. So all we're going to do now is we're going to try to find a volatility sigma such that this equation holds. So meaning again, we try different values of sigma until we find the D1 and the D2, which we then plug in such that this equation is true. And so this, of course, is really hard to do with pen and paper because this is a highly nonlinear equation. And so we need some kind of numerical optimization. So for example, in Excel, you could do that. You can write down the Black-Scholes formula in Excel and have one cell which is denoted by volatility, and then you can use that optimizer, or it's called solver in Excel, and you can say minimize that absolute difference between the actual call price which I have in the market versus what the Black-Scholes formula spits out by changing that volatility which you define in one of the cells in Excel. And so this numerical algorithm in Excel, or if you want some other software package, basically what it does is it tries different values for volatility until this equation is satisfied. Now if you do that, what you will find is that sigma is equal to 20%. And so again, you can verify that, plug in 20% for the sigma here, here and here, and you will see that this equation indeed holds. So that means that if you observe again in the market at the money call option with this price over here of $4.23.216, and that means that the volatility for these next 3 months, the implied volatility should be 20% of that underlying asset. Now we can do that, of course, for many different options in the market. Let's suppose we also look at the call option with a strike price of $90. So this call option is now actually in the money already and also 3 months left to maturity. Let's suppose the market price is $11.67.314. If again you use that same procedure as before, set the Black-Scholes formula equal to that price, solve for volatility, you're gonna get a volatility of 25%. Now if you do that for a strike price of $95, let's suppose and 3 months left to maturity, let's suppose the call price is $7.63.422, then again if you solve the nonlinear equation for sigma, then it gives you a volatility of 22.5%. And you can keep doing that for many different examples. Let's say we have an out of the money call option, strike price of $105, 3 months left to maturity, with a price of $1.85.707. That gives you an implied volatility of 18%. And then we have one more example. Let's say the strike price is of $110, 3 months left to maturity, and the market price of 65.648 cents. Then you would find an implied volatility of 17%. And again, I encourage you to actually use these values, put them into the Black-Scholes formula, and verify that you exactly get these prices. You can do that as an exercise. The volatilities basically means that we have the same underlying asset, the company XYZ, but depending on what moneyness we look at, they all have different implied volatility. Now, how can we reconcile that? Well, that doesn't actually make sense under the Black-Scholes model because, again, it's the same underlying asset XYZ, and so it should have the same volatility. So what does this mean? Well, it basically means that the Black-Scholes formula doesn't hold. And in particular, what I'm going to argue is that this assumption that returns are normally distributed is wrong. Again, there are many reasons why this might be wrong in reality. One might be these what we call volatility clustering, which I have illustrated in the data, where we have some time periods with very high volatility followed by other time periods with low volatility, and so this conditional volatility or the risk is changing through time. Another reason might be because of jumps in asset prices, and jumps are not modeled by a normal distribution, and it also could be that maybe also just conditionally returns are not normally distributed. So there might be various reasons. All we can say is that if there is a volatility smile, it must mean that the Black-Scholes formula, this assumption of constant volatility or in particular normally distributed returns unconditionally, that this thing is wrong. Just note one thing, in the previous examples I always use a call option. If you think about the put-call parity, and we talked about that in the context of Vega, then it actually turns out that the implied volatility from a call option is exactly the same as the implied volatility of a put option. And this has to hold by no arbitrage, right? Because the put-call parity didn't need any assumption about the distribution of the underlying asset, so that has to hold by no arbitrage. And then if you just take, for the Vega calculation, take the derivative with respect to volatility, you see that put and call option have exactly the same Vega, or basically the volatility affects these options exactly the same way. So if you extract an implied volatility from a call option, it's actually going to be exactly the same as the implied volatility for a put option with the same strike price. What I will argue next is that this pattern, this volatility smile, will imply that the true distribution function or of this return of the underlying asset has fatter tails here on the right hand side and on the left hand side than the normal distribution. So the normal distribution is this dark blue line over here, and the true distribution function which produces this volatility smile would be that pinkish distribution, which is kind of more pointed in the middle than the normal distribution and has too much probability either on the left hand side or on the right hand side for extreme returns. So I'm going to argue that this distribution function of returns corresponds to a volatility smile in the Black-Scholes formula. And I want to explain that with a drawing which I actually also use in the problem sets. So let's suppose this is the true distribution function of returns. Okay, so this thing should be the same as what I have shown on the previous slide. Here I've drawn it by hand, so it maybe doesn't look as nice. And now let's suppose that we first start by looking at an at-the-money option, where the implied volatility is 12%. And let's draw the normal distribution with 12% volatility, and we call this here for now this Black-Scholes PDF. That's that blue line. So that's the PDF, the probability distribution function of a normally distributed variable. So now the argument goes as follows. If you, let's say, move to a strike price of $110, that is for a call option that's going to be out of the money. If I would compute under that blue normal distribution, what is the price of the option, then I would follow that strike price and I would say, well, the option is only going to be in the money if the return of the underlying asset is large enough, and if it is anywhere in this region over here above that strike price of $110. Now, what does this mean? Well, under the blue line, there's very little probability that that's going to happen. And notice here I'm talking about these artificial probabilities, these risk-neutral probabilities. And if there is a small probability, that will imply that the price of that option is relatively low under that normally distributed Black-Scholes distribution function, which again has a volatility of 12%. Now we know that the true probability function actually assigns a higher probability of these returns realizing and therefore of that call option to be in the money. Now what does this mean? Well, under the red, true distribution function, if I have a higher probability of being in the money and therefore achieving a higher expected payoff under the risk neutral probability measure, then this means that the price of that call option is going to be higher than the price of the call option if I would assume a normal distribution with 12% volatility. Now, what does this mean? Well, if in the market I observe now a higher price than Black-Scholes price with a volatility of 12%, this will mean that if I now back out from the Black-Scholes formula with that higher price, the new volatility, that volatility will have to be higher. And in this case over here, we see that the implied volatility is 13.5% for that call option with strike price of under $10. Now we can also do a similar argument, let's say for an option with a strike price of $90. Here for illustrative purposes, it's better to look at the put option, but again from put-call parity, whether I look at put or call option, it should actually give me same implied volatility. Let's suppose I have a put option with $90 strike price. What does this mean? It means that this put option is out of the money right now. What is the price of that put option? If I assume a normal distribution with 12% volatility, so that blue distribution function, then if I assume that this is the risk neutral distribution function, then I look at this probability of returns to be small enough of the underlying asset so that that put option is going to be in the money. And that probability is just the area under that blue line. Now that's relatively small. This will imply a relatively small put price. Now what we do see in the market is that the put price is much higher, and that's because the actual risk neutral probability of the underlying asset follows that red line, and therefore assigning a much higher probability of that put being in the money. Now this again translates in a higher price than the price which we will get if the risk neutral probability distribution was this normal distribution with 12% volatility, and therefore if I take now the higher price and back out from the Black-Scholes formula what would be the implied volatility, if we now again assume that the returns were normally distributed, well then this volatility has to be substantially higher, and indeed here it will be 15.5%. Now, one pattern you see also from this picture is that on the left-hand side, if you're $10 below the at-the-money strike price, we actually have a higher implied volatility than if you're $10 above at-the-money. Here we only have a volatility of 13.5, here it's 15.5. What does this mean? It means that the red, which is the true risk-neutral probability of the return of the underlying asset, that red line has to be much larger on the left tail than the normal distribution than on the right tail. Okay, so that difference, what they indicate with x1, has to be larger than that difference between the normal distribution with 12% volatility and that red distribution. This example illustrates that if you have a volatility smile where implied volatilities are higher in the left and the right tail than at the money, this implies that the tails of the actual risk neutral probability distribution function of the underlying asset has to have fatter tails here on the left and on the right hand side than a normal distribution if you look at the normal distribution with a volatility equal to the at the money implied volatility. One example where we observe these fat tails both on the left and right hand side is for foreign exchange rates. So foreign exchange rates, they do seem to have on one side realizations which are close to zero, but then from time to time we see these really large positive or negative realizations. And so for foreign exchange options we do observe this pattern that we have an actual implied volatility smile. If you look at the data and if we compare the data, these are realizations of returns in the data to a normal distribution, we see that in the data from time to time we have foreign exchange rates changes which are really large, which are like more than 6 standard deviations away from the mean, And really that under normal distribution should never happen. Okay, the probability of that is just basically zero. But we do observe that this happens like 0.03% of the time. Similar for return realizations, which are between 5 and 6 standard deviations away from the mean. Under normal distribution, that should basically never happen, but we do see that 0.08% of the time in the data. For return realizations between 4 and 5 standard deviations away from the mean, well, that under normal distribution can happen, but not very often, so only 0.01% of the time. We do actually observe that about 0.29% of the time, so almost 30 times as often than what it should happen. If you also look at returns between 3 and 4 standard deviations away from the mean, that should happen less than 0.3% of the time, but we see that to happen 1.3% of the time, so more than like 4 or almost 5 times as often. And then finally, about 2 to 3 standard deviations away, well, here the normal distribution doesn't do an all that bad job, but then we also see between 1 and 2 standard deviations away. Here actually in the real world we don't see enough times realizations of these kind of returns, while the normal distribution would say that should be much more likely. And then finally, any realization between just around the mean or within 1 standard deviation, here if we take 100% minus all these probabilities, that's about 68%. If you do it over here on the normal distribution, we see that that should be about 64%. So again, we have in reality, we have too many realizations which are close to the average exchange rate realization than under a normal distribution. We do have also examples where we have exactly the opposite of a volatility smile. So we have here an unhappy phase of the implied volatility, where actually implied volatility is lower if you have a very low strike price, and also lower if you have a very high strike price compared to the at the money option. That on one side could imply now exactly the opposite of what we had before. So that would mean that the tails are actually thinner on the left and on the right hand side of the actual risk neutral probability distribution of the returns compared to a normal distribution of this risk neutral probability of these returns with a volatility of the at the money option. On the other side, this pattern can also be produced if there is a large expected jump. And so let's think about, again, this is the normal distribution, or for the stock price log normal. And let's think about what happens if there could be a very low average realization or a very high average realization. So basically we split that distribution into kind of two somewhat normally distributed distributions, but which are just shifted in their mean, either high or low. So how can I see that this thing implies this kind of unhappy implied volatility phase? Basically what we can do is we can construct a binomial tree with only one time step, where we either go up in the tree or down in the tree, and the up movement would basically characterize that average return which is relatively high, and the down movement would characterize basically the state where we have this low return. If you do this binomial tree and then you compute in that binomial tree different call prices for different strike prices and also put prices for different strike prices, and then you use the Black-Scholes formula, use these prices to back out what is the implied volatility, then indeed you see a pattern that if the call is very deep in the money or very deep out of the money, or the put is very deep in the money or deep out of the money, implied volatility according to these prices is going to be 0, and it's going to be the highest if we are somewhere in the middle or at the money, exactly producing this pattern of an unhappy phase in that implied volatility. Also a popular thing which we have in reality is where we have a left tail which is fat and therefore has a high implied volatility, and the right tail of probability distribution of these returns on the risk neutral measure which is thin and therefore a low implied volatility if the strike price is high. To show this again, what does this look like? It seems like that actually the realization of a large negative return is more likely than under the normal distribution, but a large positive return realization is less likely than under the normal distribution. And that's actually a pattern which we often see for stocks. So we see that there is some asymmetry, that stocks actually do from time to time have very big crash risk, and therefore have this very fat left tail. So we have some really large negative realizations from time to time. They're not very likely, but they can happen, while the upside is a little bit less prominent. Or, I mean, you do have some large returns, but not as extreme as these negative returns. Okay, so we also call this a skewed distribution. In particular here, it is left skewed. Then we could also have the opposite pattern where the implied volatility is low with a low strike price and it is high with a high strike price. That would mean that now the tail of the risk neutral probability is smaller than the normal distribution on the left, and the tail on the right is fatter than under the normal distribution. Now, in addition to computing this volatility smile, so looking at changing the strike price and looking at how deep in or out of the money a call or a put option is and figuring out how the implied volatility changes, we can also look at the term structure. So here we basically say, let's keep the moneyness fixed. Let's, for example, focus on the at the money option. And now let's look at different times to maturity. So we can look at an option with 1 month left to maturity, with 3 months, 6 months, 9 months, and so forth. And let's see whether the implied volatility of these different maturity dates changes. Now, under the Black-Scholes formula, of course, since volatility is constant, it shouldn't change the implied volatility. However, what I will show you is that there will be actually a change. So the term structure of this volatility is not constant. Now, eventually, if you put together the term structure and the smile, that will give us an entire surface of the volatility. So let's look at some examples. Consider again that stock XYZ, the current price is $100, risk-free rate is 2%, continuously compounded per year. Now, what is the implied volatility of an at-the-money call option with 1 month left to maturity if the market price is this $2.84.516? Well, again, you can plug into the Black-Scholes formula, back out what is sigma, and the annual volatility will be 24%. Then you could look at the same stock XYZ, but now look at an at-the-money call option with 6 months left to maturity, so longer term. And let's suppose that market price is $5.56.210. Here you would find that implied volatility is only 18%. And then again, if you look at another option, also at the money call option with 12 months to maturity, and let's suppose this has a market price of $7.15.707, then you would get an implied volatility of 15.5%. So you see that if you change the maturity of these options, theoretically in the Black-Scholes formula, because volatility is constant, all these implied volatilities should be the same. However, we do observe that actually implied volatilities decrease if we look at longer time horizons. Now, it's not always true in the data that volatility is decreasing. This is just in this example. But what we do see in the data is typically that the implied volatilities change depending on the maturity of the option. If we put that together, if we look at different maturities of options and different moneyness, if we think about this for a call option, this means I'm deep in the money, here at the money, and here I'm out of the money, then we can look at this combination of these 5 different moneyness and these 5 different maturities, so these 25 different options, and for 25 different options observed in the market, I then can extract always the implied volatility, and this thing we call the volatility surface. So it has this 2-dimension, moneyness and maturity. How is this useful? Basically, a trader could say, well, I know that the Black-Scholes formula is wrong, and so assuming constant volatility is not quite true. But I know that the market actually gives me prices for different options with different moneyness and different maturity. And what I can do is, let's just back out from these options which are in the market, implied volatility. And if I have to price a new option, I'm just going to use that implied volatility, plug it back into the Black-Scholes formula to find the price which I think should be fair. Now, what's the rationale here? Basically, you say, look, I take the market price, I use the wrong Black-Scholes formula to back out the volatility, but then I use again this backed out volatility to plug it in the Black-Scholes formula, and so I make a mistake once, but I kind of reverse that mistake when I go backwards to back out again the price. Now, most likely, if you're a trader and you need to price an option with a certain moneyness and a certain maturity, then you do not have already a price of an option with exactly the same moneyness and exactly the same maturity available. Otherwise, well, then I don't actually need to use the Black-Scholes formula at all anymore. I could just use that market price which I already observed. So then how does this volatility surface help me to price new options which don't have exactly, let's say, at the money and 1 year left to maturity, but let's say, for example, it has a moneyness of 1.02, so somewhere in between here, and maybe a maturity of 1.5 years, so somewhere in between here. Well, one thing how you can do is by interpolating between this volatility surface to get points which we don't exactly have, but we know it's going to be somewhere in between. And there are many different ways to interpolate. One of the simplest ways to interpolate is a linear interpolation. Now, that approach has certain limitations because it doesn't respect no arbitrage relationship all the time, and there are more sophisticated approaches to do interpolation, but for our purposes we just want to focus on the linear interpolation because it's the simplest to do and it already illustrates kind of the idea. So let's look at how this linear interpolation works and how we can use it to price options using the volatility surface. So let's suppose I'm trying to price an option with a time left to maturity given by T and the moneyness, so defined as strike price divided by current price of underlying asset given by small k. In my volatility surface, where again I use market prices to back out implied volatilities of different options, let's suppose I have an option there with time left to maturity T1 and moneyness K1. I have another one with T time left to maturity and moneyness K2, another option with T3 time left to maturity and moneyness K3, and another one with T4 time left to maturity and moneyness K4. Now what I want to do is from these four implied volatilities, from these four options, I would like to figure out what is the implied volatility of the thing which I want to price now with time left to maturity T and moneyness K. And then once I have that implied volatility, I can use it in the Black-Scholes formula to figure out what should be the fair value of a call or put option with that combination of time left to maturity and moneyness. So the way I'm going to do it is I said, look, I have two different implied volatilities here and here. And what I'm going to do is I linearly interpolate between these values to figure out what should be the volatility if I just change the time left to maturity to T, but still keep the moneyness K1 equal. So I assume here that K1 equals K2. And then I'm going to do the same thing to figure out what is the implied volatility with time left to maturity T, but keeping the moneyness K3 equal to K4 constant. And then once I have these two volatilities at these 2 points, I say, okay, now keep time left to maturity T constant, and I'm going to change moneyness between K1 and K3 and figure out what is the implied volatility if I am somewhere in between with moneyness K. Now the formulas are quite simple. They are given by these things over here. So where again sigma TK1, that is the implied volatility of this point over here, sigma TK3, that's the implied volatility at this point over here, and sigma Tk, that's the volatility at this point over here. How do I get to this formula? So if you look at the first formula over here, think about a picture like this one. So where we look at time to maturity and we plot that against volatility. Let's denote this sigma with time to maturity 1. I denote that here, sigma T1. Now similar for sigma with time left to maturity T2, that's this value. Now what I would like to find is implied volatility with a time left to maturity T, which is between T1 and T2. Now what I do is I say draw a linear line between sigma T1 and sigma T2, and I'm just going to look up the value on that linear line here in between. And the first thing I have to figure out is what is the slope of this linear line. The slope is going to be given just by the difference between sigma 2 and sigma T1 divided by, well, the difference between T2 and T1. And this is this thing over here. So it's the difference in the volatility sigma T2 minus sigma T1 divided by T2 minus T1. That gives us the slope of this line. Now I multiply the slope of this line by T minus T1, so this distance over here. That tells me, well, by how much does sigma increase as I go from T1 to T. That's this thing over here. I multiply the difference, or how much I move from T1 to T, by the slope of that line. And of course now to figure out sigma T, all I need to do is I start with the value sigma T1 and I add this thing to it. Again, this thing is just given by the slope times how much I move from T1 to T. So that gives me this formula. I start with sigma T1, I add to that this difference over here, which again is given by the slope times how far I move from T1 to T. And the same argument applies for sigma T with fixing now the moneyness K3. Here I just do it with these implied volatilities with maturity T3 and T4 with these moneyness K3 and K4. But that's exactly the same picture. I'm going to use the same idea to figure out what is now sigma Tk. So where I interpolate between the sigma Tk1, the thing which I have found over here, and the sigma Tk3, the thing which I have found over here. Just to show you again the picture over here. So what we have done before, we have figured out what are the volatilities at this point, and now I want to interpolate between these two values to find the volatility with time to maturity T, which is now kept constant, and moneyness K, which is between K1 and K3. Therefore, I draw now that same picture over here, but what I do is I plot volatility against the moneyness, where I have K1 and K3, and they denote by sigma K1. That corresponds to that sigma with time left to maturity T and moneyness K1, and with sigma K3 I denote the sigma with time left to maturity, same T, but moneyness K3. So I want to try to figure out what is the volatility if the moneyness is K, where K is between K1 and K3. So what I do is I draw a linear line. I say sigma K is equal to sigma K1. That's this bit over here. And now plus this difference, and this difference is given by the slope of that line times how far along do I move this slope? Well, as far as I move from K1 to K. So what is the slope? The slope is given by the difference between sigma with K3 moneyness minus sigma with K1 moneyness divided by the moneyness K3 minus K1. That's that term over here. That captures the slope of that line. I multiply that by how far along do I move this line. Well, I move from K1 to K. So I take that difference, I add that to sigma K1. That gives me the implied volatility of an option with time left to maturity T and moneyness K. So once I have this implied volatility, which is again between these four values which I had in my volatility surface by linearly interpolating. Then I can use that volatility now, throw it back into the Black-Scholes formula, and I have the call or the put price which I actually would like to figure out using the Black-Scholes formula. So let's look at an example with numbers. Consider again the table which I had previously, so on that slide over here. So again, we had here a bunch of options with different moneyness, different time to maturities. And now what we would like to do is we would like to price a new at-the-money call option with 8 months to maturity. And suppose that the underlying asset has a $100 strike price, risk-free rate is 1% continuously compounded per year. So how do I do that? So I say at the money call option, 8 months to maturity. Let's look at my volatility surface. Well, I do have a bunch of options which are at the money, but I don't have 8 months to maturity. But what I do have is the implied volatility of an option with 6 months to maturity and another one with 1 year to maturity. So the thing which I would like to price is somewhere between these two things. And so what I want to do is now interpolate just between these two implied volatilities. How do I do this interpolation? Basically, it's simpler than what I had before, because basically now the only thing which I have to change is time to maturity, because both of them are already at the money, so the moneyness I don't have to change. So therefore, all I can do is just use that formula which I had over here. And that's what I do here in this equation. So I say the volatility which I try to find is the volatility of the option with 6 months to maturity, which is 12%. And I add to that the slope, if I interpolate between 6 month and 1 year volatilities. The slope is given by this 12.5% minus the 12% divided by, well, I have 6 months of maturity, so 1 minus 0.5. That gives you this slope. And now, how far do I deviate from the 6 months option? Well, I'm trying to find the one with 8 months. So I have 8 months minus 6 months. So basically these 2 months times that slope. And that gives me now this implied volatility of 12.167%. Once I have for the 8 months to maturity at the money call option this implied volatility of 12.167%, now I can throw that here into the Black-Scholes formula. That's where volatility shows up here as well, and here to calculate these threshold values D1 and D2. Notice again it's at the money, so strike price and price of underlying asset are the same. I have 8 months left to maturity, 1% interest rate. Put everything into the Black-Scholes formula, either do the numerical integration or look up these values in the normal distribution table, gives me a call price of $4.28.953. Now I can look also at some other examples. What volatility do I have to use to price an option, either call or put, with 2 years to maturity and a strike price of $109? Well, let's go back to our volatility surface. So 2 years to maturities, I have a bunch of options over here, but now I don't have that moneyness of a strike price of $109. So again, the price of the underlying asset today is $100, so $109 strike price means a moneyness of 1.09. So I'm going to be somewhere in between here. Now, how do I do this interpolation? So basically what I said is, look, I have one option over here, one option over here with the same time to maturity of 2 years, but different moneyness. One has the moneyness of 1.05, the other one 1.1. And what is again the moneyness I'm looking for? The moneyness I'm looking for is 1.09. So what I do is I use this formula over here, this one, where I just change the moneyness of the option that says, okay, take the implied volatility of the option with the smaller moneyness, so moneyness of 1.05, 2 years left to maturity, that's this 14.5%. Add to that the slope between this volatility point and this volatility point with different moneyness. That's given by, well, the difference of 15.1% minus 14.5% divided by what's the difference in the moneyness? It's 1.1 minus 1.05. That's this 15.1% minus 14.5% divided by the difference in the moneyness. That gives me that slope. Now, how far do I move away from the moneyness of 1.05? Well, I want to go to 1.09, so that difference is 0.04. Then I have to multiply by that slope, and again, that entire value as how much I moved along that linear line in the interpolation, that I add to the implied volatility of the option which had a moneyness of 1.05. That gives me an implied volatility of 14.98%. The last example I'm looking at is what if I would like to price an option with 14 months to maturity and strike price of $103. So going back to my volatility surface, 14 months to maturity, that's going to be somewhere in between these two rows, and a strike price of $103, that means a moneyness of 1.03, and that's going to be somewhere between these two columns. So that's a point going to be somewhere here in the middle. Now, how do I do that? That's exactly this figure which I have over here. So I have these four implied volatilities for different maturities and different moneyness. All I have to do is now plug into these three equations, and then I get my result. I start with the option which has 1 year left to maturity and is at the money. Combine that with the option which has 2 years left to maturity and is also at the money. So what's the slope if you interpolate between these two values? Well, it's this 13.5% minus the 12.5% divided by what's the difference in the maturity. Now, how much maturity do I want? 14 months. So how much do I have to move from the 1 year maturity? Well, it's just by 2 months. 2 months times that slope. And that's the additional volatility which I have to add to the volatility of the at the money option with 1 year to maturity. Okay, so that's now the volatility which I would use for an option which has 14 months to maturity and is at the money. I do a similar thing to figure out what's the volatility of an option with 14 months to maturity and has a moneyness of 1.05. Therefore, I'm going to interpolate between these two values over here. So how do I do that? Well, to figure out the slope, I take this 14.5% minus the 14%, divide by, well, there's 1 year difference in moneyness, so divided by 1. And then I actually want to move from the 1 year maturity to 14 months. So I take 2 months times that slope, and I add that to my implied volatility of an option with 1 year left to maturity and moneyness of 1.05. That gives me now this volatility 14.083%. That's for an option with 14 months left to maturity and moneyness of 1.05. Once I have these two volatilities, what I do is I say, okay, I want to now interpolate between them, keeping constant time to maturity, but I would like to figure it out for a moneyness of 1.03, so which is that strike price of $103. So how do I do that? Again, I say, let's start with this implied volatility over here, and to that I add by how much do I change my moneyness from at the money to 1.03, so that's 0.03, and I multiply that by the slope. The slope is given by this implied volatility minus this implied volatility over here, divided by how different are they in moneyness. Well, it's 1.05 minus 1. So that's now the volatility I want to use in the Black-Scholes formula to price an option with 14 months left to maturity and a strike price of $103. Notice that if we have a volatility surface, then we also have to think about what happens to Greek letters. Why do we have to think about that? Think again about the delta of an option. The delta in particular here of a call option, tells you by how much does the call price change if the price of the underlying changes a little bit. This is now tricky. Before we said, well, okay, so we just take the derivative of the Black-Scholes call price with respect to S, and that gave us exactly that probability under the Q star measure of the call option being in the money. But now, if you think about the volatility surface, as I change the price of the underlying a little bit, then the moneyness of my option is going to change. So if price goes up, the moneyness actually goes down, and therefore now the implied volatility is going to change, and this change in the volatility is going to have an effect on the call price. So that's captured by the second term over here. It says, as I change the price of the underlying a little bit, if I increase it, then the moneyness drops. That affects my implied volatility, and our change in the implied volatility is going to affect the call price. That second term over here, that's actually the vega of an option. So if we look at Greek letters here for delta, then we have to not just look at that first partial derivative of the call option with respect to S, but we also have to add to that by how much does the call change as volatility changes, and how much does volatility change as the price of the underlying asset changes. And similar adjustment has to be made also to other Greek letters. So think about theta. Theta is change in the call price as you move through time or get closer to maturity. Well, if you get closer to maturity, look again at the surface. That means that basically maturity gets shorter and the implied volatility is going to change. So therefore for theta we would have a very similar thing. We have just a partial derivative of the option price with respect to time. So that's the theta in the Black-Scholes formula. But then we have to add to that thing again the vega, so how much does the call price change as volatility changes a little bit, multiplied by how much does volatility change as we get closer to maturity. This is important if you work with this volatility surface and you want to hedge your risks by using the Greek letters. Make sure that you don't forget how volatility changes as some of your variables which you are interested change. Another important thing which people use a lot is the VIX. The VIX is a measure of risk in the market, and in particular it measures the conditional volatility of the S&P 500. The VIX is published by the Chicago Board of Option Exchange, and so you can observe that directly in the market, and there are actually also derivatives written on the VIX, so you can actually trade that volatility measure. So the VIX has become very popular as an indicator of how risky the market is at the current time, or how risk changes through time. And it's also often referred to as the fear index. So if VIX is very high, it suggests risk is really high, and that's when people are typically scared to invest in the market. Now, how is the VIX computed? It is basically given by the implied volatility over the next month. If we look at how this VIX looks like historically, so here I plotted from 1990 to 2014, and so we see that volatility according to these options written on the S&P 500, this volatility keeps changing through time. So there are some times where volatility is low, then volatility is a little bit higher, slow again. And then in particular during the financial crisis and when Lehman Brothers collapsed, volatility went kind of through the roof. Notice that this is measured in percentage points. But again, here, if you look at volatility, it's just gigantic. It's like 80% during the height of the financial crisis. Since then, it dropped a lot. This is when also the Fed started quantitative easing, and since it has calmed down quite a bit. The last thing I want to talk about is the implied risk-neutral return distribution, which you can actually back out from option prices. And the idea is the following: we can write the call price of a European option using the fundamental theorem of asset pricing, which says that under the Q measure, the price of the call option is just equal to its expected payoff. And what is the expected payoff? Well, it says maximum of the price of underlying at maturity minus strike price, or 0, and discount that by the risk-free rate. Okay, so this expectation is taken again under this risk-neutral probability measure Q. Now we can rewrite this expectation as the sum or integral of the payoff weighted by these risk-neutral probabilities. And I write these risk-neutral probabilities by this function G, depending on the price of the underlying asset at the maturity date T. And so I sum up now everything for any possible realization of S at the maturity. That could be going from 0 all the way to infinity, and then I take these risk-neutral Q probabilities times that payoff. That's the definition of the expectation. If we were in the Black-Scholes model, then we would just assume that this thing is given by the probability distribution function of a normally distributed variable. However, now we don't make this assumption. We say, well, let's just, for some general risk-neutral probability distribution function G, let's just try to figure that out from option prices. So the way you do that is you take partial derivatives of that call price with respect to the strike price. And you take this derivative twice, and what you get is that this pins down exactly that probability distribution function G. What does this second derivative mean of the call option with respect to the strike price? This thing can actually be approximated by something which we are familiar from an earlier chapter, which is the butterfly spread. So why is the second derivative of the call with respect to the strike price given by this butterfly spread? To see that, let's write down first the first derivative of a call with respect to the strike price. That would be the call price at the strike price plus some small variable d minus the call price at the strike price and that time to maturity t. That would be the first derivative, or if you want, you could actually also write this as the call price at the strike price and t to maturity minus the call price at the strike price minus a small number d and maturity t. Now the second derivative can now be just written as the difference between these two things. It says, well, the second derivative is buying a call option with a relatively low strike price, buying another call option with a relatively high strike price, and selling two call options with an intermediate strike price. And that's exactly the definition of a butterfly spread. So the risk-neutral probability, where the price of the underlying S at maturity T is exactly equal to K, can be written by that price of that butterfly spread divided by that number delta or D squared and times the gross return of the risk-free rate between small t and the maturity date capital T. And this is quite neat because if you have enough different call prices with different moneyness, then you can actually get a probability for the price of the underlying ending up at many different possible values at the maturity date, and these probabilities are under this risk-neutral probability measure Q. Notice that, for example, options written on the S&P 500, you basically have strike prices with $1 increments. So you do have quite a lot of different options with a lot of different strike prices, and therefore you can estimate this risk-neutral probability measure quite accurately from these call options or put options on an S&P 500. So if we are able to get all these risk-neutral probabilities, then we basically can use them in the fundamental theorem of asset pricing for any kind of payoff. So we can price any kind of derivative using then these probability functions. Again, what is crucial, you want to estimate that only if you actually have enough options traded, so with many different strike prices. Otherwise, you cannot get these probability distribution functions for many different values. and so then it's not very useful. And of course, you also want to make sure that there's enough liquidity in these markets so that the prices which you observe are actually the true market prices and not just some random thing which maybe just two people in the entire world trade at some point in time.